Okay, for your information, this lecture will be recorded, and I will upload it later to a YouTube channel, so that if you miss something from the live session, you can again watch it on the channel, and the links will be provided to you by NPTEL team. Okay, so I'll start. In the first lecture, in the first week syllabus, I think there were few topics, that is algebraic sets, just introduction, and second it was, I think, rings, of course commutative with unity. It's ideals, that is both, not both, prime and maximal, and I think radical was introduced. I think these are the three things that were introduced by Professor Dilip Patil in your classes. Okay, so I was thinking about doing some problem sessions, like I will give you a problem, you can try it for 3 or 4 minutes, then I will explain in detail. So it is a 2-hour long class, so we will have enough time. So yeah, first of all I want to know that if you attended the classes, so that you can if you are not able to talk, then you can just write it, just a yes or no. No. Okay. What about two other people, Vaishnavi and Ritik? Actually your voice is breaking. You can just write me yes or no, so that I can just explain for 5 minutes, then I can start. Okay. Okay, I'm assuming that you haven't, since I have only gotten one response. Okay, so first of all, our in the whole class for today, K means an algebraically closed field. We know what is a algebraically closed field, right? That it will have every polynomial. Okay, so an algebraically closed field is something, if you take any polynomial from here, from kx, x is a variable, then there exists small a, okay, such that f equals to 0. I mean, it contains all the roots of f for all f belongs to kx. So it's kind of a like nice field. We don't have to worry about the roots, existence of the roots of a polynomial. So in general, you can define an algebraically set without algebraically closed field. Only field is enough. But let's not get into those trouble and simplify as much as possible. So, and algebraically, uh, uh, an alg an algebraic set is a zero set of a polynomial. It would be better if you just yeah, I will just I'm trying to follow the syllabus, so I think the professor will explain what is extension and contraction in upcoming classes. So after that, I think it would be better for me to talk because I have to maintain the syllabus. Because but see, for this week's syllabus, I only have one class. If I don't talk about these things in this class, I will not be able to talk in future. So I hope you understand. Okay, an algebraic set is a zero set uh, of a polynomial in kx1 up to xn. I'm writing this ideal. Actually, it would be better if I just write a zero set of finite polynomials so that they are equivalent, right? Because if you know what is a Noetherian ring, then by Hilbert basis theorem, kx1 up to xn is Noetherian ring. So every ideal is finitely generated. So an ideal equivalent to finite polynomials. So in bracket it is ideal. So I'm not writing in a formal method, just to revise you or just to give you a intuition of the problems I am about to do. For the formal introduction, you should watch the lectures. It is very well explained there. Okay, so some nice example. If we take uh, polynomial ring in two variables, and suppose I take an idea, I take a polynomial say x1 plus x2 equals to 0. So and I should denote this. If my ideal is I should denote this as vi or zi. I think vi is standard. So this is my x1, this is my x2. So v of f, how would it look? That means the zero set of this polynomial, and we know that think x1 plus x2, it should be x1 minus x2 from R2, or A2 is fine, where we just A2 means an affine plane, and affine plane is nothing but you can say that it is R2 or C2 or K2 field, but we ignore the idea of origin fixed to 0. That means it has origin, but it necessarily does not need to be 0. That this is your k2, right, or c2 in suppose, sorry, say r2. But we can think of an affine plane like this, where this is my new origin. This maybe you can think of your a2, like it has origin but it need not be fixed to 0. Okay, now yeah, what should be the 0 set? Then I think it should be like this. So for finite number of polynomials, I have said that if you are given f1 and f2, what should be the 0 set of this polynomial? That is it should be the points x1 x2 from a2 such that both f1 x2 and a2 of x1 x2 equals to 0, right? So you can think that you can see that when we define for more than one polynomial, the points in this algebraic set should satisfy both the polynomial. So similarly one can define for finite number of polynomials, right? You can get x to xn an, and it should be if I 0, it should be L for all I greater than equals to 1 to L. Okay, so you can see the pattern behind this definition, repeated pattern of behind this definition. So I said that ideal and finite polynomials are same thing for a Noetherian ring, Noetherian polynomial ring. So if you take any ideal from standard notation I should use xn, then v of I, and we know that I can be generated by these finite polynomials L, then this is same as fail, but this is I mean this I am saying that this is claim, but v of I is all those points again such that f of x1 up to xn 0 for all a belongs to I. So I'm claiming this to be equal, but by definition we can see that this equality is not at all, they are not equal, right? Because there are only, you are checking over finite polynomials, but you are here you are checking over all the polynomials between inside I. So can anyone tell me that how they are equal? If not, it is fine. Just try to think about how a ideal is formed. Like, what do we mean by this? How does the element look like in I? And if you can think about that, then I think you will get your answer, because K is field, right? But that is integral domain. So if a product of two number is 0 there, then one of them has to be 0. Now can you give any intuition?
So, hello.
Sorry?
Can you hear me?
Yeah, I can hear.
So, I will be like, it will be the linear combination of F1 to Fn, right?
Yeah. So you are saying that if I take any polynomial from AF, it would look like some linear combination of these, right? I equals to not I, say Ri, but I can
Yeah.
again take those Ri minus 1 components to inside AI and note it as AI dash, so it is fine. We can write it as this, right? Am I clear?
Yes. Yeah. Yeah.
So you can write it as linear combination of this. So now you can see that if uh, say f belongs to I and f equals to this, then we can just get our so better to do a direction wise thinking, because suppose my how would I say this, suppose my x belongs to v of f1 up to fl, then I can see that for every f belongs to I, f should be fx should be I equals to 1 l aix fix, right? And this is already 0 because x is coming from this. And how did I define this? That is, this is say your x, and this is 0 for all I, right? So here this is 0 for all, right? It doesn't matter what value we get from ai of x. So you can see that it should be x should be inside uh, v of f, then at least this direction you are getting, that is v of f1 up to fl inside vf. Now for the inverse direction, this is quite again not f I. So for the inverse direction, again you can just think of that if x say x dashed belongs to vi, then fi of x dashed should be 0 for all I, right? Because fi are already in I for all I. So yeah, x dashed should be v of. So these are all like routine checks, but I'm just saying these things because so that you can get familiar and get hold of the basic facts, that is this this is the thing. So okay, now I think we should do our first problem. We know the operations on ideals, right? That is also explained in the first class, and I am assuming that you know this, that for two ideals I1 I2 of, it is a commutative ring with unity, it is possible to add them their intersection, and one sec. Okay. So, and third of all is that I1 I2. So, and these are all ideals. This is only ideal when you talk about commutative ring. It's not true in non-commutative ring, but I cannot uh, explain everything in this class. So one simple thing to notice is that I1, this product is in intersection. So all these operations are possible in uh, if we say the set of all ideals in A. So it has plus this intersection and this product. Now also we have defined what is an algebraic set. So first problem, V I1 of I2 is V I1 union Vi of E, and this is a B V I1 plus I2 V I1 intersection V I2. So can you guys try this for 1 or 2 minutes, and I will be back. Hi, can anyone give me any hint or something? Okay, so I shall start. I think. So for the first proof, you can see that if my x belongs to uh, vi1 union vi2, then you will see that either let either x belongs to vi1 or x belongs to vi2. So suppose x belongs to vi1, so you can see that that is for every f belongs to i1, f of x belongs to 0. And now how, like, if you take any element from i1 i2, how would it look like? So it would look like g of, say, h I k I should want to say L, and hi belongs to i1 and ki belongs to i2. So you see that if x belongs to vi1, then hi of x equals to 0 for all I, right? Then one can see that g of x equals to 0. So, and g was arbitrary, right? So x belongs to v of i1 i2. So similarly, one can show that okay, I think I will just do it. Now let y belongs to z of ij. Then if y doesn't belongs to z of I, then there exists a polynomial in I. Okay, I was using the notation I1 I2. There exists a polynomial say f in I1 such that f of y is not 0, right? But for all polynomial g of I2, we have f dot g of y equals to 0, right? Because fg belongs to I1 I2 for all g, right? So this is actually pointwise multiplication, so you can just write this So this is uh, 0 for all the polynomials from G, right? So there are so already you know that f of y is not 0, but so this is not 0, but k is an integral domain, so g of y is 0 for all g of I2, right? So your y belongs to z of I2, that is y belongs to z of I1 union of z of I2. So I started with y doesn't belongs to I1. You can similarly start with y doesn't belongs to z of I2, and you will get that y belongs to z of I1. So you are again getting another direction, so we are done. So for the second part is similar thing, but I think I should leave it as exercise because I want to introduce to you Zariski topology. So for that okay, we have time, so I think shall I prove it or leave it as exercise? Can anyone respond to me? If it is easy to you, then I can leave it, or if you need to see the rigorous proof, then I can do it. Let's make it interactive so that I know that you are getting or you already know. I can get your like how you are perceiving this course. Anyone? Okay, so I'm assuming you need it. So for B, let x belongs to V of I1 plus I2. Then we need to show that it belongs to satisfies all the. So now we know that I1 belongs to 0 belongs to I1 plus I2, right? So for every f belongs to I1, f of x is 0, right? That is x belongs to V of I1, and similarly x belongs to V of I2, that is x belongs to V of I1 intersection V of I2. Now the converse thing is again similar. You can just take from there, and how do the look how the elements of I1 plus I2 look like. So it actually looks like h plus k. So if both the x belongs to from both V of I1 and V of I2, you can just so if y belongs to V of I1 intersection V of I2, then g of y should be h of y plus k of y, then it should be 0. So we are done. Now the like interesting thing is that I told you what is an affine space. an affine n space, and we will introduce Zariski topology. Wait a second. Okay, so affine n space is like is a vector space where we just kind of flexible about the origin. You can think of that. It's actually geometric space where a vector space is an algebraic space. Like their algebra is the primary operation, and in affine space geometry is the primary like concern. So now how do I want to define a topology on an? So I'm assuming that you guys are familiar with the point set topology, because for this course basic definitions and operations from point set topology is needed. Do I need to introduce what is a topology on a set, or you guys are familiar with the definition? Just yes or no in the chat would be fine. Like, do you need it? Do I need to explain it? Surya, do I need to explain it? Anyone? Vaishnavi? Okay. So, okay, topology on a set, because a set can be both finite and infinite. So rather than speaking as a space, I think it would be better if we just consider a set. So a set say X, suppose tau X the subsets from X which satisfy following prop. So you already know what is union and what is intersection. Arbitrary union of any subcollection from tau X, arbitrary union of subsets from any subcollection, not subcollection, arbitrary union of subsets is inside tau X. That is, tau X is closed under arbitrary union. Tau X is closed under arbitrary union. Tau X is closed under finite intersection and 3, both phi and the whole set belongs to say like this, belongs to tau x. Now what do you mean by closed under finite intersection? If we take any finite set of subsets, finite collection of subsets, then their intersection should be inside this tau x. uh, all three if tau x satisfies all these three properties, then tau x defines a topology on X where elements of tau x are called open sets and X tau x is a topological space. So similarly, if we think about its counterpart, one can define say I'm saying that tau x c by y belongs to tau x. That means y is a subset of x. Actually like this, y complement, that is x minus y, where y belongs to y belongs to tau x. So one can see that tau x is closed under finite intersection, finite union, closed under arbitrary intersection, and obviously x belongs to tau x, so phi belongs to tau xc and phi belongs to tau x, so x belongs to tau xc, phi and x belongs to tau xc. So in a similar pattern, x tau xc is a topological space where elements of tau xc are called closed sets. Now we'll be using this second like idea, this complement of this tau x thing. This now let me cut this part. And paste it here. Okay. So you know that n is an affine n space, and I want to define a topology on n, and you know what is an algebraic set, right? So just now if we take the tau n c as, I'm defining this v of I, your I is coming from, I is an ideal of k x1 up to xn. We define this way, right? Elements of vi are from an, where x1 up to xn are independent variables, so they will cooperate with here n coordinates. So now try to see that if these subsets satisfy these three conditions. So already you have seen this result, that is V of I1 union V of I2 is V of I1 product I2. Now you know that this operation of product is only possible up to finite times, right? There is nothing called infinite product in algebra. So if I just take finite union, at least we know that it makes sense up to finite union, so that is enough. You will see that. So this tau c of an is closed under finite union. Now second, if we take arbitrary intersection ij, j is from say 1 to infinity, we'll see that this is true ij. Now infinite sum of ideals makes sense. How? That obviously in usual algebra infinite sum does not make sense. It makes sense in a part where it is called a completion of a ring, where you can just make sense of infinite sum. But in usual algebra, that is we are learning here, you can just take finite terms to be non-zero and others are zero. But that was not possible in product, right? Because if any of the term was zero, then the whole element should be zero. But here you can just take that a1 up to a2, this and choose like this is non-zero, this is non-zero, and say others are zero. So see that defining infinite sum of ideals is possible. So this taking arbitrary intersection is possible. So up to second condition it is true. Now see that if phi and an belongs to this tau cn, turns out it is possible. If we take v of 1, that is unit ideal, that contains all the polynomials from kx1 up to xn, and there is a theorem, and this is from Eisenberg's book, that you can see that only only phi is a solution for all the polynomials. You can just prove it by induction formula, but I won't do that here because I don't recall now and I did not prepare for this. But this is not tough. One can just simply put an hour of thought and see this is happening. And the next one is trivial. Just zero ideal has all the points as its solution. So you see that all these three properties are satisfied by this set. So an tau c an forms a topology on an. It is called Zariski topology. Zariski topology on an. But we'll in future study this Zariski topology thing, and turns out that Zariski topology is much weaker than the usual topology. It is not even horse drop. That means you know that for any two distinct points there is just an open neighborhood which differentiates them, or at least this uh, this diagonal thing is closed inside this product. But anyway, we will see this in future. For now I think it is enough for now. uh, Now we will do some uh, now we'll do some problems. Okay. So one way to learn Zariski topology is from this affine space, and is it clear up to this point, or you have any questions? Because it is 1 hour. You can just write to me. I will take a 5-minute break and then we will start with the problems. Okay. Okay, so one way to uh, learn about Zariski topology is studying these polynomials and studying its solution sets in affine space. And uh, other way is like, how do we connect this algebra and geometry? So affine space and its Zariski topology are in uh, algebraic geometry part, but all those famous quotations that how does it connect with a polynomial to a say ring, or and I mean by ring I mean ring by commutative ring with unity and its ideals. So that is quite intriguing and non-trivial. but you see that this Pekar set of all prime ideals, this analog of Zariski topology, you can define in Pekar. I think it would be better if I just define Zariski topology and spec of R, because Pekar is already introduced by Dilip sir in the first week material. So maybe we can just get introduced to this Pekar thing, and for last half an hour I will discuss some algebra problems. So because I just told you the definition of topology and gave you an construction of Zariski topology on affine space, so I think it would be interesting for you. Now, okay, so R is ring, commutative ring with unity, and already you guys know what is a prime ideal, so I'm not wasting your time on that. So says Pekar is P is an ideal such that P is a prime ideal. Now I want to construct a topology on Pekar. So how would I do that? Again, the same procedure, that tau C of Pekar. But here my element should be V of I, and I haven't told you what is V of I. That is, V of I is set of all prime ideals from spec of R such that I is contained in P. That is, all prime ideals containing I, or you can say that spec of A by I, right? This is interesting because you know that there is one-on correspondence between the ideals containing I and ideals of A by I, right? So it turns out that it is also true for the prime ideal correspondence, that is, prime ideals containing I are same with the ideals of prime ideals of A by I. But we can see this later. Anyway, so these are the sets where your i's are any ideal from R. Now, but this would require some standard results from commutative algebra. Now I am thinking if it is right to do it now, because all these results will be true. Finite union should be V of I1 up to In, and V of Ij should be V of J, and thirdly phi should be, and Pekar should be in this tau C of Pekar. Maybe I will do this in next class, because I think that you would need some standard results, that if any ideal is contained in union of prime ideals, they should be in one of them, and if a ideal contains all of the prime prime ideals, it should contain one of them. I think these theorems you would need. uh, okay. Okay, so maybe start with some assignment problems. For each problem I will give you 5 minutes, and if you respond to me with an answer, it is good. If you don't, then just I will start doing it. And please respond so that I will get also motivated, and I can give uh, extra effort from that motivation to bring you uh, bring the best out of me. Okay. Okay, so the first problem is uh, assignments practice. mm. So the first problem is find all the ideals in each of the rings. Also mention which of them are prime and maximal. I am not defining them here, but you can just I hope you already know these things. Ten, Z of 25, and CQ. So you have 5 minutes, so I'll start explaining them at 7:10. You don't need to do it like explicitly. If you do, that is fine, but if you don't, that is also okay. You can just start with hints or like intuitions. Okay, can anyone tell me the answers or partial answers or hint? Okay, so for part A, now what is an ideal is an abelian subgroup, but these are all abelian groups under addition. So yeah, Vaishnavi.
Yes, like here every ideal will be principal, right?
Yeah,
Okay.
uh, I mean for uh, ideals are like um, I'm not sure if every ideals are principal, but yeah, for Z18 it should be every ideal are principal, and also Z5, Z25 also every ideals are principal. Yeah, you are right. And can you tell me which are the prime and maximal ideals? Because these are not uh, like these are not integral domains, right? So these are and first two are not integral domains, but the third one is a field. It's a field.
Yes.
So the
For third one, like 0 and Q will be the only ideal
yeah,
for Q.
yeah, and zero is
So
both.
0 will
Yeah,
prime and maximum.
yeah. So zero is prime and maximal ideals, and Q is trivial ideals. So we are kind of ignoring the trivial ideals, right? And okay, so coming to A, so first we have to see the which are proper subgroups. So can just think about the multiples of a number, right? Like what about we take 0, 2, 4, 6?
2Z 18 and 3Z 18 would be the prime as well as maximal ideals, right?
Yeah. 3Z, 2Z. I mean, yeah, what am I writing? Up to 16, it is 2Z. You can write it just,
18.
yeah, you can just write it at 18. And should be 3, 9, up to 15, should be 3Z 18. So one thing is that and again there are 4Z 18, uh, 5Z 18, all of them are there, but you need to make sure that if they are ideals or not. But anyway, uh, so again you see that 4Z 18 is contained in this thing. 6Z also 6Z is contained in both of them, like this. Okay, but anyway, so these are all subgroups, and you see that uh, you see that if they are closed under scalar multiplication, that is arbitrary multiplication, not scalar, but you see that all these are subrings, but and also there are ideals also, but what about the maximal ideals or prime ideals? And you see that this thing that z18 by 2z18, it should be what, z by 2, right? 2z, that is z2, and z18 by 3z18 should be z3. So these are all fields, right, as well as integral domains. So 2z18 and 3z18 should be maximal and prime. And if you check about other these multiples, say that you will be getting z4, z6. So these are not integral domains, right? So they are not prime ideals, and obviously not maximal ideal, because maximal ideal is a prime ideal. Now what about b? Similarly, you can think about b, right? Z of 25. So the trick is to finding this all those divisors. 18 has 2 3, not 4. I don't know why did I write 4. 2 3 6 9, but here only 0 and 5 and 25. So 0 and 25 are again same thing in this z25. So you see that 5z25 is an ideal, right? And you see that this is, I mean, if you take the quotient, z5, so this is a field, so 5z25 is maximal and prime. So thank you, Namrata, for this notation. Otherwise I would keep writing these whole things. This is actually easier to explain and easier to eye also. Okay, so going to next problem. Okay, can we do this? Find all ring homomorphisms from phi, from z by 6z to z by 15z. Again, you can take 5 minutes and we can discuss after that. Can anyone tell me that?
Only two, right? Identity and the trivial one.
Yeah, only two ring homomorphism is possible. That one is zero homomorphism, that is the trivial
Yeah,
one,
in the
and by
identity.
identity you mean?
As in, yeah, one goes to one.
Okay.
Like we just have to look at where does one go, right?
Yeah. That is
That
the
will
trick.
determine the homomorphism.
Yeah, but is it one going to one? I mean, we have to be little careful about that, because phi of 1 dot phi of 1 should be phi of 1.
Yeah. So there are only two elements that satisfy this property. Like a square is same as a in Z modulo 15.
Yeah, what 15. So there are two elements, that is k equals to 0 and 10, right?
Hmm. Yeah.
So
Yes. Okay. Yeah.
now can you
Even
sorry?
one also does that, right?
um,
Like k square is k, so I can have k to be 1.
so you are saying that phi of 1 goes to
1.
1.
10 square is 5 modulo 15, right?
Sorry?
Sorry. No, no.
Okay, suppose your 1 goes to 1, then what you see is that uh, phi of 6, that should be 0,
Hmm.
but it is 6, but 6 is not 0 in,
Mm-hmm.
right?
Hmm.
So phi of 1 cannot go to 1. I mean, not coming from this operation, but uh, if this,
No, but how did you get that? Okay. 0 is same as 6. Okay.
oh, that is in Z6, right?
Yeah.
Yeah. So yeah, now I think all the doubts are clear, right?
Yeah.
So okay, thank you, Namrata. What about others, Ritik, Surya and Vaishnavi? uh, yeah.
Hello.
Yeah, Ritik.
Yes, sir, I get it. I get it.
Yeah,
That there's
yeah,
two.
yeah, yeah. Okay. And Vaishnavi?
Yes, like can we define like this phi of take some class
Okay.
to phi x phi of x is 5x.
So the trick is to define trick is to that you have to actually find where does 1 go, because Z6 is generated by 1, right? You just take uh, a finite sum of this, then you get all the elements. So if you know where is 1 going, then you know the whole root map of this homomorphism, right? So like determining phi of 1 in Z15 gives us whole picture of phi. Because if you take m from Z6, obviously m is from 5 to 0, then you see that already phi 0 should go to 0, that is fixed, right? Because this is also abelian group homomorphism, so phi of 0 plus phi of 0 should go to phi 0. From here you get this. Now phi of m should be m times phi 1, right? Because you take 1 times up to m and you get this. So getting phi 1 is enough for determining this morphism. And uh, and also there is another trick is there, that is you already know that, okay Namrata, from here we can just eliminate our 1. So you see that let phi of 1 goes to k, then uh, phi of 6, that is phi of 0, that is 0, so it should be 6 dot phi 1, and that is 6 dot k, and that is 0 in Z15. So you are getting we are getting a relation in Z15, and from this you can see that only possibilities of k are 0, 5 and 15. I have solution set with me, so I can write it quickly, but you can calculate easily to see this happening. And using your argument, that is k square equals to k in mod 15, you can again eliminate you can again eliminate 5 from there, because 25 minus 5, 10 does not divide, 15 does not divide this, so k not equals to 5. So I think we have the whole picture, right? So only possible cases are k equals to 0 and 10, that is phi of 1 either 0 or phi of 1 is 10. Now Vaishnavi, is this clear? I mean, is this what you are asking?
Yes, it is clear.
Okay. So one question was there that I was planning to do, but it will be too lengthy. That is, how many ring homomorphisms are there from Zm to Zn? That should be the GCD of their GCD of m and n. But it's a standard solution, so I'm not doing it. Rather, I would do some. Okay.
Hello.
Yeah.
One more thing I wanted to ask. This is not regarding the problems that we are doing right now. The
Okay.
assignment 2 that is shared in the this no in the portal. In that there are two questions, but the second one doesn't actually is a question. Isn't a question. Like it's just given the like it's like a result is given there, so it doesn't look like a question. Nothing has been asked in there. So what do we do? Like only one.
In assignment,
Yeah, in the assignment too that
uh,
is shared.
I haven't looked into assignment yet, but if nothing is there,
Hmm.
uh,
There are two sub questions under that question, and then first one is fine, but the second one is just a result. Like nothing is asked as such to find out.
I mean,
I will.
if nothing is asked, you should just prove that statement, I mean, if it is a trivial statement, then it is fine. You can just
Oh,
write it again. But if it is uh, like like this, an integral domain has uh, 0 as a prime ideal. If like these statements are given, then you should prove it.
okay.
Again, I haven't seen
Okay.
that. Uh, maybe mm, can you mail me on this regarding this? I will then. Sorry.
Okay, you.
Yeah, I'm writing
I
that
wanted
one.
your mail ID.
Yeah, this thing also.
Okay.
Another one is there, but this is on my mobile, so that I can see when you send.
Okay.
Okay, just
Yeah. Thank you.
yeah, sure. um okay, again, this is a standard result, but uh, I think we should do it. 2, 3. Let R be an integral domain so that if the only ideals in R are 0 and R itself, then R must be a field. So one thing is that we know that a field has only two ideals, but what about if you are given an ID, then what about the converse? If you take 5 minutes, then we can discuss.
Yeah, 0 will be the maximal ideal. So if we take the quotient, then it will be isomorphic to R, which is the field. So that will look that
Yeah,
result
yeah,
you
yeah,
can use.
yeah. Actually, the trick is if you take any non-zero element, it will form an ideal, right? If you just take the multiples and so
No, we given that these are the only ideals, not 0 and R itself. So the 0 has to be the maximal ideal because there is no other bigger ideal than that. So if 0 is the maximal ideal, then R
yeah,
over 0.
yeah.
that will.
That is I mean, here we are assuming a result, what Namrata is saying, that every ring has a maximal ideal. uh, so I was kind of avoiding that, because if you use that, this is like,
Not this one, the standard one, the R over maximal ideal is a field.
no, first you have to assume this, right? Every ring has a maximal ideal
No,
from
why do I need to assume that?
uh,
Because zero itself will work. I'm given that zero is an ideal, right? So, and there is no bigger ideal than zero, which is not equal to R. So, zero has to be the maximal ideal
but
by the definition
yeah,
of.
yeah, sure, but for that you have to assume that a ring has to have a maximal ideal, right?
Why?
uh, because suppose I am saying that R does not have any maximal ideal, so you only have the data is that 0 is prime ideal because it is integral domain, right?
See, I'm given that the only ideals are 0 and R. So by if I go by the definition of maximal ideal, what does it say that an ideal
No,
is said to be
that
a
is
maximal
fine.
ideal if there is in between ideal
No,
from
no,
that
no.
ideal to
Yeah,
R.
yeah, I understand your what you are saying, but everything is fine. That what is the definition of but uh, for 0 to be a maximal ideal, because maximal ideals are proper, so R cannot be a maximal ideal.
Hmm.
But R has to have a maximal ideal, right? You are already assuming that R already have a maximal ideal, right?
But in this argument, I don't see that I'm using this
No,
this
no.
result anywhere.
See, okay, let's forget about this problem. So, there is a standard theorem that one can prove by using John's lemma, that every ring has a maximal ideal. So that you can, we just take that for granted that that if some of the if all the ideals are given from a set, then there is always a maximal ideal, right?
Yeah.
Yeah, but uh, the proving that every ring has a maximal ideal uh, is not trivial. Like you learnt in the linear algebra that every vector space has a basis, right?
Even Sir has proved this in his video.
Sorry.
Sir has proved this.
Yeah.
Proves this. Yeah.
That is fine, but I was trying I was trying to avoid this theorem,
Okay.
because actually if you don't, then there is another solution, but it is fine, what you said is fine, but uh, for this this result is needed, that is only I am saying. But it is good that you used this argument and did this in a minute, it is very good. But anyway, but yeah, you need to use this result. Also for your reference, I can refer you, you can just see theorem 1.3 from Atia MacDonald. Yeah. So by ring again I mean commutative ring with unity. This is good, this is good. Yeah. So discussing this result, we actually get a bigger result. And also uh, I have another solution, but okay, uh, another approach is that to show that as it is integral domain, uh, you already know that it satisfies most of the properties of a field. Only needed to show that every non-zero element has an inverse, but that is also easy to show, that if you take a not equals to 0 from R, then I of A is an ideal, but only two ideals are possible, and it is integral domain, so it is non-zero, so I equals to R by assumption. So you are seeing that one belongs to A, that is A dot R dot A equals to 1 for some R belongs to R, so A is a unit. But the first proof, what Namrata said, is much more trivial, so we should stick to that everything has a maximal ideal. So by that result, R cannot be maximal because it is trivial, so 0 is maximal. So R is an ID, R is a field. Okay, now think time is almost up, so I will be giving a small problem. Okay, problem 4, that is okay, let's do this. Let's see how much we can go. Let R be a commutative ring, just ring, because we are already assuming that it is commutative. An element A of R is nilpotent if an equals to 0 for some n natural number or positive integer, so that this nil rad for A belongs to R equals to 0 equals to n is an ideal of R. So you have already been introduced to radical of an ideal, right? Radical of an ideal is all A belongs to R such that, better to write xn belongs to I for some n, not to z. So by this, can you see that radical of the zero ideal is nil radical? Also we will see in future that radical of an ideal is intersection of all the prime ideals coming from V of I. I told you now what is Vi, that is P from spec R I of P. So actually what is nil radical then? It is the intersection of all prime ideals, right? Because you see that every prime ideal contains 0, so it is actually a stronger like personality or stronger subset. I don't know what you say. So is actually the smallest subset that is contained in largest subset that is contained in every ideal, or you can say largest ideal that is contained in every prime ideal. So from there you can just see that when we say that spec of A is isomorphic to spec of A by nil radical, but that is because all the prime ideals here are already in there, because nil radical is contained in every prime ideal. But the good thing is that A may not be reduced. But A by nil rad is reduced. By reduced I mean it has no nilpotent element. All these things will be useful in future, but I just gave you all this just these are motivations. There is no like deep involvement here. I think this is fairly clear because you have already seen that intersection of all prime ideals this is, and also this is fairly clear from the definition, because radical is defined via this and nil rad is defined by this. So yeah, I think there is not much time for the this proof. Maybe you can just try it yourself, so that so okay, let's see one by one. So I denote my nil rad as like this from Atia MacDonald notation. So first of all we have to show that it is closed under multiplication. If AB belongs to nil rad, then you know that AM equals to 0 and Bn equals to 0 for some Mn belongs to n. Now if you take LCM of them, because R is commutative, LCM of Mn, you will see that it is LCM of Mn be LCM of Mn to 0. So yeah, so this is closed under multiplication. And also for the negation of I mean, if it is abelian group or not, you can see that it is n. Again, a to the power n equals to 0, so minus a is also in eta.
Hello.
Hello.
But you need to show this closed under addition, right? Like a plus b.
Yeah, I'm coming to that. And in fact, only non-trivial thing in this proof is to show this.
Yeah, you can take the sum of m and n.
Yeah.
Because it is an integral domain, so the binomial we can do binomial expansion and
Yeah. In fact, just we have to take yeah, you have to be little careful about choosing k. K should be bigger than equals to m plus n minus 1. So better choose k equals to m plus n minus 1. Then you will see that we will be getting j equals to 0, m plus n minus 1, m plus n minus 1, j, a to the power j, and c to the power m plus n minus 1 minus j. So you see that after when j is greater than equals to n, obviously it has to be smallest integer. When is n smallest, so when j is greater than equals to n, then what should be the so minus j should be less than equals to minus n, so m plus n minus 1 minus j should be plus n minus n. Minus 1. Yeah, so when your j is greater than n, then you see that j is greater than n implies a to the power j is 0, right? So we don't have to worry about this sum up when j is greater than n, but when j is less than n minus 1, you will see that in a similar way minus j would be greater than 1 minus n, and again your m plus n minus 1 minus j should be greater than m plus n minus 1 plus 1 minus 1 minus n greater than equals to m. So when j is less than equals to n minus 1, then you will see that c of m plus n minus 1 minus j is and this thing is greater than m, so it should be 0, right? Because c to the power m equals to 0. Oh god. B. And for now, just consider a to the power n equals to 0 and b to the power m equals to 0. So this is clear, right? When j is greater than equals to n, then a to the power j equals to 0, and when j is less than equals to n minus 1, then this entity is 0, right? So you are seeing that for every summand of this direct sum becomes 0, because already taken care for all j case, right? Is it clear? Is it clear, Vaishnavi?
Yes.
Yeah. So that is how you see that a plus b also is in this nil radical thing. So you have shown that it is an abelian group and it is also closed under multiplication, so it is an ideal, right? And for abelian group, I think it is enough to show a plus b and minus a belongs to the ideal, and for abelian group and ab belongs to I for ideal. So these three conditions satisfy uh, satisfy the possibility of ideal. And okay, so we have proved that a nil radical is an ideal. Anyway, okay, so I have already given you my email ID, that is just my name and my title, no space, nothing, just @gmail.com. You have any doubt or any doubt about the classes? I don't think I can help about the classes, but any doubt about this session or any doubt in general problem relating to these topics, you can just mail me. Okay, thank you everyone. Bye.
Can I ask just one question?
Yeah, sure.
Yeah. So suppose I have A. A is a ring, and I want to know how many ring homomorphisms are possible. Like, what are the ring homomorphisms from AX to A? So other than evaluation map,
uh,
do we have any other?
you mean from AX to A?
Yeah.
So there is always trivial one. You are
Yeah,
saying
that is the evaluation at 0.
Okay.
No, not 0. No, that would be evaluation at 0.
That would be
this.
identity map, I think.
Yeah.
So first of all, you would have trivial homomorphism, and X equals to A for all belongs to A,
Hmm.
and I think, yeah, because a ring X is generated by
1 in X. Yeah.
So it is enough to take care for only these two. And in our ring homomorphism definitions, we always say one goes to multiplicative identity goes to multiplicative identity. So 5 of 1, 5 of 1, but this is your integral domain. So 5 of 1 should go to 1. So only thing to care about is where is X going. So I think this is enough. I'm a little tired right now.
So only the
Sorry?
So only the evaluation
Yeah,
maps.
only the evaluation maps, I think, for now, but maybe there's some trick, because you know algebra is always tricky. Okay. If I get any other answer, I will get back to you. Okay.
Yeah. Okay. Yeah. Thank you.
Thank you. Okay.
Thank you.
Thank you.